in a minute if you want.
Okay, give me a sec. I accidentally opened Fusion instead of searching for Fusion.
Nice.
Oh,
All right. That's everyone from the waiting room.
I think there's one more. I'll bring him in.
I hit him to join, but
Gotcha.
gonna give it just a couple more minutes just in case anyone's running late, and we'll get started. All right, we'll go ahead and get started here. So I'm Bernardo, and then George is also with me. We'll be co-teaching this class together. Um, I'm assuming you guys know this, but this is the Finite Element Analysis Milestones course, and we are with ASME. So this is the section that basically the American Society of Mechanical Engineers Club here at Purdue is teaching this, or for this session. So yeah, so as I said, I'm Bernardo, and then George is our
I'm
other.
George. Yep. Go ahead, Bernardo.
We're co-instructing the course, so we'll switch off instructing. There may be days where one of us is gone and the other one is there. But if you guys have any questions about the course, like assignments or anything that we went over in lecture, feel free to either chat one of us today in Zoom, or I guess call us over in actual class when we're there next week, or through Slack, things like that. So let's get in a little bit into ourselves. There we go. So I'm Bernardo. I'm a sophomore in mechanical engineering, and I'm also doing a minor in electrical and computer engineering. And then I'm from Brazil, and I have experience in these CAD softwares, NX, which I learned in CGT 163, Fusion 360, Inventor, and SolidWorks, which those were kind of a combination between doing an internship and then just clubs and ASME here. And then my experience in FEA is in Fusion 360. I know there are other FEA softwares you could use. We'll talk a little bit about them today. The most common one is ANSYS. That's more of a professional one, but Fusion 360 was the one that's taught in this course because it's the easiest one to learn for first-time users. And then also it's available through Purdue, so that's a plus.
As for me, my name is George. I'm a sophomore in aerospace engineering, although I'm planning to go to mechanical engineering by the end of this semester. And I'm an international student from Indonesia. And my CAD experience are in NX, Fusion 360, and SolidWorks. Similar to Bernardo, I took CGT 163, so that's where NX came from. And then I actually got introduced to Fusion from ASME. I took their CAD training class and sort of explored Fusion myself from there. And then SolidWorks I used back in my community college. So yeah, that's that. And then as for my experience in FEA, similar to Bernardo, it's in Fusion 360, and I can completely agree with Bernardo on the fact that Fusion is the easiest FEA application to use, especially since a lot of students here in Purdue use Fusion 360. I feel like they'll have a better understanding and they'll be more familiar with the Fusion space. Okay, go ahead.
Yep. Okay, so this is our attendance QR code. We'll have one of these each week. Make sure that you guys fill this out, especially for this class, since we made attendance mandatory because we want to make sure that everyone is actually going to complete this course, because there are other people on the waiting list who would want to come in. So yeah, we'll just complete this every week. If for some reason 1 week you don't come to class and you watch the video, or you just look at the slides after class, just make sure you fill this out every week, because we are supposed to report this back to the Milestones office, and to get the certificate, you are supposed to attend all 5 classes, whether that is through, online after class watching the video, or actually being in class. Although we highly encourage all of you to be in class, as this class will be a lot of hands-on activity. Not this first one specifically. This one is more of us just talking at you. But after that, for the next 4 weeks, it'll be pretty intense. Like, we'll be getting hands-on activities to do in class, which are mostly the assignments, but you'll get time to do those in class, and we'll be there to help. So it's really useful if you guys actually come in person. If you did not get this, it will be in the video, and I will also send out this link later in Slack. So I'm going to keep going. So what is Milestones? Yeah, since you signed up for the course, you're probably gonna check. I'll send out a link to this code as well later in Slack. I'll also send out the link to the Slack later before we all leave, so that way you guys can access it. You should be able to scan it with your camera as well, like your phone camera. So what is Milestones? You guys probably know as you're signed up for the course itself, but Milestone is basically just a series of skill-based workshops. There's CAD training, there's coding with Arduino, there's Python, there's FEA, and It basically supplements your coursework. So this is a no credit hour class. You will not get credits for it, obviously. And with that, it's a lighter course load. It's not supposed to make you feel overwhelmed. So if at any point this is making you feel like it's too much, come talk to one of us. We'll be happy to help you and kind of go through the problem and kind of help you fix whatever's going on. And then upon completion of this, you guys will get a digital certificate from the College of Engineering. And the certificates are usually issued about a month after final exams from each semester. So for this class, since you guys are session one, you will have to wait most likely until mid-June to get them. I know last semester's got released like mid-January, so about a month exactly. So the course objectives for this class are to understand the importance of FEA and finite element method empirically, which is something we'll go over today. And then we'll teach you how to use the necessary tools to perform structural analysis of a 3D model through a computer, specifically using Fusion 360. And then we'll kind of go over how to display the results in Fusion 360 in a simple but meaningful way. We'll learn tools like compare and other tools in Fusion 360 that allow you to kind of see your results in a way that you could either present them or you could understand them by yourself. And then we'll also learn how to implement improvements. We'll do we'll later on talk about this, but just improvements to the 3D model itself based on results of the actual like structural analysis and the FEA that you guys will run. So the structure for this course is 5 lectures, 5 modules. The first one is basically an intro to FEA and the Fusion 360 interface. Second one, we'll talk about static stress analysis. We'll go a little bit more into how to create a mesh in Fusion 360, which is like a really basic skill, something you have to do for every single analysis you run. And then the third class, we'll talk about mesh improvement and ways that you can better understand and better your model as a whole. The fourth class, we'll talk about post-processing and 3D model improvement, like I talked about. It'll be mostly related to understanding results and how to display them, and then also learning that 3D model improvement. And then the final week, we'll do a final project. This week will be slightly shorter, just like today's class. It'll be mostly time to work on your guys' final project in class. We'll be there to answer questions and things like that. So yeah, there's one course project, and then these are the dates and when we are meeting. Leave that on the screen just for a second. Okay, so the course project description, we'll go over this more in detail when we actually get to the project, but it's basically just creating a 3D model or using a pre-existing one that you already have created to basically perform a static analysis. And from there, you'll be able to suggest improvements or run an analysis to improve the model. And then it's really simple. It shouldn't take that much effort. It's basically a comprehensive project of everything you will have learned in this class. So getting into the intro to FEA and just general interface. So what is CAE? CAE is basically computer aided engineering. So it's just using computational calculation power, which, for FEA is really required because it would take forever to do these calculations by hand to basically simulate approximations or really, really close approximations to real life problems. Sorry, it's taking a second. And what is FEA? FEA is finite element analysis. And it's basically a simulation of a given physical phenomenon. In our case, we're going to be using forces on a wrench object. And it's basically a numerical technique from the finite element method, which is basically, you can do a lot with finite element method. It's just a component of solid mechanics, and it can be done by hand. It's just extremely long, and to do it for an object like the one we will use as an example is very, very tedious and very, very long, and it's much easier to use a computer to do so. But you can basically do static analysis, which is the one we're going to be mainly focusing on, dynamic analysis, where loads are changing, buckling analysis, where there's deformation going on during the application of the force, and modal analysis as well. So this is kind of an example. We'll use a more simplified object, and I'll send that out to you guys before next class for our basic analysis for the assignments. So what's the difference between FEA and fluid mechanics? Basically, the CFD, or computational fluid dynamics, focuses on the surroundings influencing the object, and FEA deals about how a surrounding effect deals on or influences the object's behavior. So a force applied on, say, a wrench that you are twisting, and you can basically calculate a lot of things, but the main three things we'll focus on are the von Mises stresses, strains, and the displacement. So how much it will, a part will bend when you apply force to it. And similarly to FEA, CFD actually relies on the FEV, which is or FEM, sorry, which is the finite volume method. That's just a picture of the CFD analysis on a ball. So how does the finite element method work? Basically, any physical phenomena requires mathematics to really understand and quantify what it's going to do to a part or object. Sorry, it's taking a while to flip through these for some reason. And these are mostly described using partial differential equations, which some are basically impossible to solve, and you need to use approximations to do so. So these complex equations need to be solved to create like relevant quantities for the phenomena that you are applying to the force. And we'll do that in really small sections, which you'll see when we create meshes, what that's like. And you basically can predict the behavior of a part or an assembly under specific conditions that you define within the program, which can be anything of the sort like structural or fluid behavior, thermal transport, wave propagation, and growth of biological cells, which probably not as applicable in this course, but it is something you can do. So I want you guys to think about the way you calculate the area under a curve. Basically, you just divide it into tiny little, this is a video, but for some reason it won't play on the slides. I think we've all seen this before though. It's just like creating boxes underneath the curve, and you make those boxes infinitely small. And then from there, you can get a really, really good approximation of the area under the curve. This is very similar to what FEA does on the computer. You basically will create a mesh, which is a bunch of tiny little triangles or squares, or however you define the shape, and you'll make these as small as possible to get as accurate of a result from your simulation. And with this, there's a lot of factors that you can change that we'll go over later. But if you have, say, a corner, this will need to that will need to be more precisely simulated. You can make in that corner the mesh or the area really, really more fine, and you can like really understand what's going on there. So a little bit about the history of FEA. The actual mathematical, like the FEM, the finite element method, was created by these three: Leonhard Euler, I'm gonna butcher this, sorry, Carl Schellbach, and then Richard Courant. They've basically created the mathematical equations that would be able to really simulate what would happen to a object or a part. And then with that, computing kind of came along, and people created computer simulations of these, like the one we'll use in Fusion 360. And these were kind of made by these 5 individuals here. Argyris was considered technically the first like modern computational like FEA inventor, I guess. So applications to FEA, I'm going to hand this off to George now. He will be teaching for this portion.
Thank you, Bernardo. So yeah, let's click through it. And let's give it a sec. Okay, so again, you see the wrench as earlier. So a couple applications of FEA, as you can see on the left, includes vehicle suspension elements, wing structural components. So really, FEA can be utilized in a lot of different majors, as you can see, not just mechanical or aerospace, and not even just civil, right? But if we want to take a look at it at the automotive industry, well, the most common ones I can think of, and probably you can think of as well, is like crash testing, right? So in aerospace, we could also, of course, we need to think about whether or not our plane can withstand a certain load, right? And on the right, we see why FEA is very helpful, very useful for us today. And that's because it allows engineers, manufacturers, big companies basically to test out models and assemblies without having to spend any money at all. They can just simulate it in their computers, and this significantly reduces the cost and time and makes a more efficient engineering process in general. Next slide, please.
There we go.
Thank you. So, of course, there's a lot of FEA softwares, and if you see there, Siemens, SolidWorks, Fusion 360, major corporations, they tend to have their own FEA softwares, and of course, they all come with their pros and cons, where each software would prefer files from their own CAD software, but it's not necessarily required. We're doing so because we know that Purdue students, we have access to Fusion 360, and as part of our fifth session, we would require you guys to make your own projects. It would integrate way better if you guys made it in Fusion 360 and just simulated it there as well, right? But as you can see, the two big ones, ANSYS Fluent, ANSYS Workbench, this is a more professional ones. These are the softwares that you tend to see in the industry, but we won't touch on that. We'll be looking at Fusion 360, but a lot of the knowledge and how to set up the system to simulate will also be able to be carried over if you guys end up looking, studying FEA more and getting into ANSYS. Thanks.
Sorry, it's taking a second when I click through it.
You're good. Yeah, so one very important thing about FEA or FEM is what's called as meshing, right? So meshing is basically taking the part you have and sort of breaking it down to smaller components so we can analyze parts of it and not just the entire big part. And what that helps us do is sort of get a better approximation, a better analysis of whatever part, whatever model or assembly we're looking at. So could you click through that thing? Yep, there you go. Yes, so if we look at that, this is our part in Fusion, right? Before we simulated anything. And then we can see this is what it looks like. Sorry. Yep, all right. There on the right is what it looks like after you apply a mesh setting, right? So we're gonna get into that in the coming weeks, but right now, just to give you a general overview, if you could move on about like 2-3 clicks. Yes, all right. If you can see, as the mesh gets smaller, our analysis actually gets more and more accurate, but it does come with a cost, and that is the simulation now will take very long to load, and oh boy, it gets bad, guys. But further along the course, we'll see how decreasing the mesh actually affects our results, and also, yeah, the time it takes for our computers to run the simulations. Next, please. All right. So, of course, when we're analyzing our part, we need to be specific, right? What materials are we using, and all that. We can set that up through Fusion itself because they have settings. As you know, you usually apply a material to your part when you're done making it. So that's exactly what we need to do when we're doing our analyses. And also similar to like all the engineering courses you could probably think of, like statics, dynamics, you would also have to sort of specify where the loads are, like what forces are actually acting on the system, what we want to test out. And in this class, of course, we are looking specifically at static stresses. Okay, so this is what it looks like. Here are the important information about the material we would need to apply to our parts. Because of course, if you change the material, our analysis is going to be significantly different. Next.
Just a side note, we're going to be using aluminum 6061 for all parts in this course. We'll talk about this later, but yeah.
Alrighty. Okay, so as Bernardo mentioned earlier, FEA works by like a huge system of partial differential equations. Also comes with us interpolating the analyses over the small elements we analyze from the meshes. And also we'll be taking a look at how we can sort of look at our results and be like, oh, well, that's a good result, you know, like our part will work under these stresses, under these loads. And if you click one more time, Bernardo. Okay, two more. Okay, wait, can we stay here? Sorry. So another thing I was about to mention is how we're going to simulate how certain forces will act on a part and using animation so we can actually like clearly see how certain loads will affect the physical structure of our parts. And we can see as well, like example, if we have a load somewhere, we can see which parts of our model experiences the most load and which parts like don't experience any force at all. And next up, so here's an example. If you click one more time, Bernardo. Yes, so yeah, it's really weird. But if you guys see the blue, yes, if you guys see this, this is basically what our model would look like under no stress. And earlier, if you guys see, yes, this one over here is what it looks like if there's a force sort of pushing our model there inside the big hole. You can see a bit of deformation there, and you can see the minimum and maximum values that just tells us at what area, thanks, Bernardo, thank you. It just tells us what area experiences the most force, as well as the displacement that comes with it. As we can see, we're looking at a particularly small model. So if you look at the displacement, it's very small, but the simulation actually sort of stresses it so we can see what further stress would look like on our model. And just a quick like side note. So if you can see on the left there, we have displacement. We'll be taking a look at three major things during this course, and those are the displacement, safety factors, as well as the, missing one. Displacement, Bernardo, which one am I missing? Yes, the von Mises stress. Okay, but we will get into that starting next week, so you guys don't have to worry about any of that right now. All right. Next up. Yes, so I mean, of course, after doing the analyses, you want to sort of improve your products, right? Improve your models, improve your assemblies. And one of the ways we could do that is by shape optimization. What that actually lets you do is sort of this system where it will try to analyze your part or model, and they'll sort of like give suggestions on what you could cut down, like maybe change your material or sort of change your model a bit, where you cut bits and pieces of your model to help reduce cost as well as decrease safety factors. So if you guys can see on the right there, the safety factor is 15, and it says, you guys read it, the design appears to be over-engineered. That's because the usual safety factor that we're looking for, especially in this course, is between 1.5 to 3. And so, as you can see, in the recommendations part, shape optimization will remove unnecessary material, and of course, they'll ask you if you want to just switch to a cheaper material, right? So that's the sort of things that we will get into during this course. And I think, yes, okay.
Yeah, so before we do this downloading portion, I'm going to go over, why is it not letting me click it out of this? There we go. I'm going to go over just really quick kind of what an FEA analysis really looks like. So this is, as you can see, there's a lot of studies. These are all from actually this class, but basically this is our part right here. I will send you guys an actual like file for this right here. But as you can see here the mesh that I just talked
Bernardo, I think we're still on the presentation.
Oh, hold on. Sorry about that. Do you guys see it now?
Okay, yeah, that looks good.
Okay. So as you can see here, it's basically just the model, which I'll send to you guys later. But this model, we'll use it for the entire class. But this is kind of the general layout from when you click here you go from design to simulation. And right here, you can kind of, it just automatically pulls whatever model you had in design into here, or whatever assembly you had. And to create a study, you basically just go up here and you would click study. And then there's also a ton of other things we will talk about in the coming classes, constraints, loads, things like that. But then if you guys, just as an example, the results you can see, I just clicked results up here on this tab. We'll talk about that also later, but as you can see here, you can see the deformation, and this is actually kind of exaggerated. Obviously, with something that would deform 0.1 millimeters, you probably wouldn't notice it this much. So actually, it's like that. And this is the normal model, so it's barely noticeable, but this is just exaggerated so that you can see it. And as you can see here on the right side, this bar right here, there's all the different things you can analyze from the results of the simulation. We'll mainly be going over these top three, which are the safety factor, the von Mises stress, and then the displacement of the part. So for today, there isn't really much more that we will be, go back to the slides, click, that we will be going over. However, I would like to just mention, if anybody came in late, to please, I'll send the attendance link again on Slack. So please fill that out so we can make sure that you guys are still wanting to do this course and that you will continue with it, obviously. And then if you guys do have Fusion 360 installed and you don't have any questions for me or George, we will most likely be ending it right here. However, if you do not have Fusion 360 installed and you want help with step-by-step instructions, just stay on and we can go over these with you. We're kind of assuming most of you have Fusion, but if you don't, that's also okay. And like I said, today was a kind of shorter class. There's no assignments for this week. So next class, it'll be much more hands-on. It'll be a lot more of you guys actually doing instead of us just kind of talking at you. So yeah, feel free to head out if you already have Fusion and you don't need any help installing it or you have no more questions. Otherwise, yeah, we'll wait, hang around for a couple minutes if you do need help. Thanks.
Hi, Bernardo and George. I have a quick question.
Yes,
Yes.
go ahead.
I messaged you guys. I was a co-op student. My main question is about workload. What kind of assignments do we have? I kind of missed the first 10 minutes or so.
Yeah, so there's no assignment this week, but from here on out, you'll have an assignment basically every week. There's 1 week there are 2 assignments, but like we said, we give time during class for this. So we, most of the times, simulation times will start to get kind of long towards the later parts of the class, but you should be able to complete most, if not all, of the assignment in class. Other than that, truthfully, I wouldn't expect more than an hour a week. And then maybe on the last week of the final project, maybe 2 hours for that, as it's a little bit longer. But yeah, it's not a huge time commitment.
Gotcha. Thank you.
Yeah.
Yep.
So wait, how do the assignments work? Is there a place to submit?
Yeah,
I'm
so
new to
we'll
this
create
whole milestones thing, so
so we'll create a Google form like we did for the attendance to submit them, and then we have they'll get dropped into a Word document, and you'll be able to you can see it here. Like we'll have a template that will show you guys how to use it and stuff like that.
gotcha. Sounds good.
Yeah.
And I know today it was through Zoom because of XYZ.
So we'll be recording through Zoom. So we can we'll send out the link as well for those who want to watch it live.
Perfect. Yeah, that sounds good. For me, I prefer live just to get me on track. But yeah, I'd appreciate that.
Yeah. For the others, do you guys want me to go through how to download Fusion 360?
I just would like to know, like, it says that it wants me to join a team or something.
Oh, yeah, so you don't can you share your screen really quick?
Yeah, give me a second.
I may need to give you permission. Hold on. Try it now.
Okay.
Yeah. I would okay, you don't really need to do this, but it's just like the team is basically like a folder. So if you were to do a project, like I know for ASME, we have our own ASME team, and within there, everything is there because it's like a Google Drive, if that makes sense. So I would just like create a team for yourself, and you're basically just gonna be like, it's just gonna be your files. It's just a folder for yourself. So I would input whatever you want for the name real quick.
Oh, okay.
Yeah.
And then after that, is that basically it? Like,
It should be. It should bring you straight to Fusion from there.
oh, okay, cool. Thank
to
you.
like the main. Yeah.
All right. Yeah, that was just the only question I had.
Okay. Awesome.
All right. Thank you. Have a good night.
You too. All right. In that case, you were able to get it installed.
So we are good to go, right?
Yes. That will be all for
Yep.
today.
Sure.
Yep.
Thank you.
Yeah.
See you.
Nice.